Okay, good afternoon, everyone. I hope you had a lot of interesting talks on Spark already. This talk will not just cover Spark, but also some other technologies. So we'll be talking about stream processing in a more general sense. A little word about myself and the company I work for. I'm a lead data scientist at Clario. We do open source software integrations, so we're a system integrator. We build platforms using open source technology like DCOS, Kafka, Spark for analytics, Flink, and basically any open source tool that fits good for a certain use case. Besides that, I also do a PhD at the University of Ghent, where I do research in how stream processing frameworks work, how they compare, and how you can tune them. And I also help teaching a course on Apache Spark at the university. So a bit of context to the talk of today. I'll be talking about stream processing frameworks. Many have been developed over the last decade and the last years. Some examples are Storm, Apache Beam, Flink, Heron. But now the big question is, how do you decide which one you're going to use for a certain use case that you have at your company? So today I chose 3 frameworks that I'll be mainly talking about, which is Spark Streaming and the newer structured streaming API of Spark, as well as Kafka Streams, which is a library made by the developers of Kafka to wrangle data residing on a Kafka cluster. And finally, I'll also be talking about Apache Flink. Flink has been gaining a lot of traction in the stream processing community. It's one of the newer frameworks, but now also already has been around for quite a long time and is being used by many very large companies. So a disclaimer before I start comparing these things is that there's no all-round winner. That's not the purpose of this talk, and it should not be the purpose of any benchmark to choose one framework that fits all solutions, all use cases. So what I'll be going through is more some kind of thought process to what you need to look at when you choose a framework for a certain use case, and that depends on what use case you have and on the requirements your use case has. So there are some things that they all have in common, which is they're all distributed frameworks, which means they use several machines to process data. Because they do that, they can handle larger amounts of data, and they're used for massive data processing. They're used for near real-time or real-time processing, and they can help you with doing ETL and analytics jobs on your data. It's quite difficult to structure a talk like this and keep it interesting and not go over endless lists of things you need to keep in mind when you look at stream processing. So I'm going to pick out 2 use cases that are fairly different, but that probably ring a bell to most people in the audience here. And we'll try to figure out how you can decide what kind of frameworks work for these kind of use cases. So the first one is a fraud detector, and the second one is a platform monitor. For the fraud detector, what it basically does is it tries to detect fraudulent transactions in a large stream of data that comes in. So imagine you're a bank, and in your pipeline you need to score using a machine learning model whether a certain transaction is probably fraudulent or not. You would do that by doing some feature computation, then you score it with the machine learning model, and that machine learning model is periodically retrained in batch to keep up to date with drift. So the requirements of an average-sized bank could look something like this. So imagine you have 400 million transactions per day that you need to score, and you get a time budget of around 500 milliseconds to do this. These are most of the time very tight SLAs because you need to be able to process all the transactions that come in a certain time budget. In this case, that's 500 milliseconds. So the second use case, which is fairly different, is a platform monitor. This is a type of component that runs on most platforms. What it does is it gathers platform metrics such as CPU, memory usage, I/O, and it computes some KPIs on it, like averages and other interesting KPIs that you want to know about how your platform is behaving. So here we have 50 million metrics per day, and the time budget is a few seconds. You will be triggering alerts using these metrics, and humans need to interact with dashboards, so you don't have latencies of millisecond levels. A few seconds is enough. So before we start, there's an important question that we need to first ask ourselves, which is, do we really need stream processing, or can we handle this in some other way? Not every use case requires a fancy stream processing framework to do the work. if we look at our two use cases for the fraud detector, you're computing KPIs, you use scoring with the machine learning model, and you have a lot of custom logic of business logic that you're implementing for your certain bank or tool. So there you would say that if you need a lot of custom logic, using something like a stream processing framework will help a lot there. For the platform monitor, on the other hand, you're computing averages over windows, you're doing some easy transformations, maybe some easy descriptives. Some of this is possible by just doing SQL queries on a database. If you're just showing some averages and whether or not it's above a threshold, you can do that with SQL queries on or using something like Prometheus. You don't need to use stream processing necessarily. But for the purpose of this talk, let's suppose we decide we need a stream processing framework, and let's go through this process of what you look at when you make a decision. So I listed 3 broad categories of things to consider. The first one is performance, then you also have advanced features which the frameworks offer, and finally deployment and internals. So let's start with performance. I listed 2 important questions for performance. The first one is how much data does it need to process? And the second one is does it need to be fast? So if we think about how much data a stream processing framework needs to process, we think about the term throughput. So throughput is the rate at which output messages are emitted from the sink of a framework. And it actually is a kind of an indicator of whether or not you need a distributed system. If you have a very low load, there's no need of setting up an entire cluster and doing things in parallel if it can be easily handled by one machine. One thing that needs to be kept in mind there is what will the future look like, because at the moment you may have a low load, but it's possible that your company is growing at a very rapid pace and that the load of data that you're processing is also increasing quite rapidly. In that case, if you think it will be ramping up to a certain level in the future, there may be a need to already start using distributed frameworks right now to prevent having to switch in a few years. So if we look at our 2 use cases, for the fraud detector, we had 400 million messages per day, which is about 5,000 messages per second on average. This is quite some load. This is, for a stream processing job, already quite something to handle. So most people would use a distributed framework for this. Especially since it's possible that we get peaks throughout the day or going up to 30,000 messages. So if you need to be able to handle big peak loads and still be able to reach all your SLAs, then distributed systems can definitely help. So to give the example here where you have an SLA of 500 milliseconds on your P99 latency, if you start running behind on your processing, your latencies will ramp up very fast and you will not be able to make it anymore. For the platform monitor, on the other hand, this is a constant rate. You do not have any peaks. You just have 50 million messages per day, which is 600 messages per second. And you have the same types of metrics right now as within 1 hour. There are no big fluctuations in the amount of messages you have to process there. So there the throughput is much less. All of these frameworks should be able to handle this kind of throughput. All these frameworks are made to do distributed computing, and they're made for massive data processing. So it's kind of their bread and butter of what they should be used for. So there are no large differences on the throughput side. So back to the other performance question that we have is, does it need to be fast? Does it need to be fast? For some use cases, this is a very important thing. For other use cases, this does not matter that much. For example, the fraud detector is something where you have very tight SLAs. There, your P99 latency is 500 milliseconds, so you will need to be able to process data at a very rapid pace. The platform monitor, nobody really cares that much if it's 900 milliseconds or 1,300 milliseconds before you see a certain value on a dashboard. You just want to have the data in a reasonable time frame. So the term that we use to describe this is called latency, which is the time it takes to generate an output from several inputs that you use to do your computation. Latency depends on some different things, but 2 of the most important things are listed on this slide. So first of all, the type of transformation that you're doing will influence your latency a lot. To give an example, most frameworks implement something called tumbling windows, which means that you buffer data of a certain time frame, for example, 5 seconds. At the end of the 5 seconds, you do some computation on that data. For example, you compute the average of everything in that bucket, and then you send it to your output sinks. In that case, your base latency will always be half of the window length. It will always be 2,500 milliseconds on average. The reason for that is that you're constantly buffering, right? So many of these transformations that do buffering will add base latency to your framework or to your job. The streaming model you use is a second important factor, but this is only important in case you do transformations that allow you to just push data through at a rapid pace without doing too much aggregation like tumbling windows. The two most important types there are event-driven frameworks, which are the most intuitive. They process data in records. As the records come in, they process the record and send it out again. While micro-batch frameworks buffer at the receiver side, so they wait for data to come in, they form a buffer, and then they process that buffer of data. There are some advantages for doing that because you can optimize things better if you work in smaller batches, but it of course also adds a lot to your latency. The time you're buffering is time that is straight added to the amount of time that the entire computation will take. Not every use case requires you to have very low latency. So for example, for the platform monitor, a micro-batching framework like Spark Streaming will work okay. Structured streaming is the step of Spark to try to get more closer to continuous processing and to event-driven processing. So for the event-driven side, you have either Flink, Kafka Streams, or continuous processing for structured streaming. This is something you would use for your fraud detector, for example, because there you really have those low latencies that you need to get. So if we go on with the table that we started, you see that the fraud detector, probably Spark Streaming, would not be the best choice because it does micro-batching. All the other frameworks offer event-driven processing at the moment. So these might be more adapted for this use case. Okay, let's go over to the second category, which is advanced features. There are 3 questions here. First one is who will build it. The second one is accurate ordering important? And the third one is what is the ecosystem like? On the question who will build it, we'll be talking mainly about the APIs that the framework offers. So there are quite some differences here in what these different frameworks offer you. Spark Streaming offers Scala, Java, and Python and is quite high level. They took it to the next level with structured streaming, where the API got even more high level and is now really easy to read and really intuitive to program in. They still offer Scala, Java, and Python. For Flink and Kafka Streams, there are lower level APIs available and intermediate level APIs. So low level APIs, you would use that if you have a job for which you really need to get down to the state of the application and you want to be able to modify things there or access the lower state. This is not necessary for many applications, but there are some cases where you really want this, and then you would use something like Flink or Kafka Streams sooner than you would use structured streaming, for example. Flink and Kafka Streams are now also offering SQL APIs called KSQL for Kafka Streams and Flink SQL for Flink. But these are less mature than the ones offered by Spark. So if you look at our 2 use cases for the fraud detector, which is most of the time built by a data science team, they prefer higher level APIs in general, and they like working with tools like Python to do machine learning, and because they feel most comfortable with that, because they do their batch modeling already with Python. Platform monitor is something that is more a task of data engineering team. Or an SRE team. What they would do is prefer lower level APIs because they're more well acquainted with tools like Scala. Python would fit there as well. So if we look at the table, we could say that for the fraud detector, structured streaming with their higher level APIs is a very promising tool for data scientists to be able to score their models or score a stream in real time using the models that they developed in batch. Let's go over to the second question, which is accurate ordering important? This is where it gets quite critical for many use cases. There are different types of handling a stream and using time as a characteristic of the stream. So to give an example, if you have different observations coming in, like number 4, 7, 8, and then 10, and you want to bucket them in windows and do something like compute averages on them, if you would use a time characteristic called processing time, number 4 would end up in your first window, 7 and 8 in the second one, and 10 in the third. So the way this works is if the data comes in, it just puts it in a window, it lets time progress. If a new one comes in, it puts it in the next window, and it just looks at the time that the system itself has. It does not look at what kind of observation it is or what the observation describes. In the case of delayed data, so if your number 8 comes later than it actually should have been because there was network congestion or because the sensor went offline and came online again, then it's possible that this number of 8, for example, ends up in the third window instead of in the second one, which is actually wrong. It should have been in the second one, but there were some small issues. So the way you can counter this or you can solve this is by using event time and watermarking. So what this is basically is that you do not look at your own system time, but you look at the timestamp that is offered by the observation when it comes in. So you look at the event somewhere contains a timestamp, and based on that timestamp you decide in which window it should be. So if you do that, number 8 would end up in the second window still because you see, oh, okay, this was actually a bit too late, it should be in the second window. What a watermark is then, it describes the ultra bound on when it should still consider an observation or not. If you do, for example, averages on windows, you will need to wait a while before you can give your output if you just want to give output one time at the end. So if you say, I allow observations to be 1 second late, you'll be basically waiting that 1 second before you're able to output that observation. So that watermark gives you a bit of buffer on how late data is allowed to be, but it also adds to your latency. The time characteristics offered by these different frameworks are Spark Streaming only offers processing time, so they don't have event time. You would need to implement that yourself, which is quite cumbersome. It's quite difficult to get this entirely correct. They took a step further with structured streaming, where they do offer event time. So you work with data frames that are built up continuously, and you just specify which column contains the time. And based on that column, you do your event time processing then. Flink and Kafka Streams also offer both event time and processing time, and they work in quite similar way as structured streaming. So you just define where in the record your timestamp is, how long you want your watermarking to be. You can specify watermarks per operation, so for certain joins longer than for the aggregation that comes after it. There are some extra things here that you can read upon if it interests you. If you look at our 2 use cases for the fraud detector, getting out of order data can be quite a problem. You are computing features. If some events end up in wrong windows and your features and model outcome depend on that, it can give you missed fraudulent transactions. So you could there, for example, update old windows. For something like a platform monitor where you're trying to correlate metrics, you could also say that using event time would be more a preferred option because you can see better when the event really came in and what the correlation between the different metrics is. But here it's less important. You could use processing time for something like a platform monitor as well. So like we said, Spark Streaming is actually the only one that doesn't offer event time. This is also closely related to the fact that it's micro-batching. So if we want to use event time for both these use cases, we'd probably reside to something like structured streaming, Flink, or Kafka Streams. So the third question of this category is, what is the ecosystem like? This is a question which needs to be adapted to the use case that you're trying to answer. It's different for every use case. What I'm trying to get at here is what kind of things are offered out of the box by the framework. For example, connectors to databases that you want to use. Is there a close integration with a batch layer, and do you really need to do a lot of batch processing around your streaming jobs? Are there connectors to messaging layers? Like, for example, Apache Kafka, if you have Kafka as a message broker, is it easy to get data from Kafka and put it back on there? For this use case, since we are looking at a fraud detector, which is closely related with the batch retraining cycles that you do for your machine learning model, we'll talk about the batch APIs of these frameworks. So for Spark streaming and structured streaming, as you all know, there's a very strong batch API. It's actually a batch framework doing streaming as well. There are a lot of libraries that you can use for feature extraction and for modeling. For structured streaming, the API that you use in streaming is very similar to the batch API, so it's not a big of an obstacle to go from a batch programming to streaming, which is very nice. For Flink and Kafka Streams, on the other hand, this is slightly different. Flink offers a very limited batch API and also limited machine learning. They are even refactoring their entire machine learning library at the moment, moving a bit more towards Spark. They also use pipelines and with these types of stages that you now have in ML pipelines in Spark. Kafka Streams does not offer any batch API. It's actually really meant to process data residing on Kafka. And since Kafka is most of the time used as a real-time message broker that offers you like an intermediary between message producers and consumers, it's focusing on real-time data processing and has no batch API. So for our fraud detector, Spark and structured streaming offer good options there because they offer lots of things out of the box. For the platform monitor, this question was not entirely relevant because we don't have batch there. So there we still have all options open. Then the final category is deployment and internals. So there are two important things here that I'll talk about today. First one is how do we want it to run? And the second one is what if a message gets lost? So how do we want it to run refers to what kind of deployment options you have. Do you run it on a cluster, and if so, how? For Spark and Flink, you use master-slave architectures. So you have a master which assigns tasks to the workers, and they execute those tasks. There are some different options, like using standalone clusters, or you can rely on the cluster managers of Mesos or Kubernetes if you're running, for example, on DCOS or on Kubernetes with your workloads. One thing there is that clusters have idle time if you don't use them and require maintenance to go along with version upgrades, which is just something that gives up some overhead on development. Kafka Streams took a different approach there. What they actually do is you have your Kafka cluster and you just spin up containers containing Kafka Streams applications, and they connect to the Kafka cluster, and that cluster then gives them certain partitions of topics that they need to read from. So if you want to scale up or scale down, you basically just add a new container and your load gets distributed over those extra threads. So you do not have a master slave there, you just have different threads all connecting with the same consumer group, and that way your Kafka cluster knows they all belong to the same application. The fact that Kafka Streams takes this different approach it's quite interesting, because if you're, for example, implementing some smaller application like a platform monitor and you do not have a Spark cluster running or a Flink cluster, it can be quite a big overhead to have to spin up an entire cluster to just do some platform monitoring. So in those cases, using something like Kafka Streams is actually quite practical. You don't have all these overheads. It's easy to spin it up and get it down again. For something like a fraud detector, which is really the core business of your company, it wouldn't be a big issue to spin up a cluster for something like this. The second question in deployment and internals is what if a message gets lost? So what if a message gets lost? If something fails in your system and you lose messages, is this a really big issue, or is it actually not what you want, but it's quite all right? For something like a fraud detector, this is a very big issue. If you're missing transactions or or not doing scoring on every transaction, you can lose customers, and this can really be a big problem for you as a bank. Your platform monitor, there you rather not, but if you use lose one CPU metric somewhere over the course of time, it's not a big disaster. Probably no one will ever notice. So the message delivery guarantees that there are actually threefold. You have at most ones, which means if you have some failure, messages get lost. So that means it fails, it comes back up and just starts processing again, and it doesn't really know exactly what it already processed and what not. At least once means it's possible that it processes stuff 2 times, so it keeps in mind what it already processed and what not, but there are some cases where things might get processed 2 times, and exactly once is actually the ideal, where you process everything once and only once. Exactly once always comes with a lot of small letters on things like side outputs, because there are some frameworks that offer you exactly once end-to-end, because they know whether the sync saw or did not see a certain message with some certain ways of how they handle that, like two-phase commit protocols and other things. But if you do side outputs, like for example, somewhere in the middle of your application, you're writing to a database, it's very difficult for many frameworks to know whether that part of user code really got executed or not. So those are parts where exactly once is actually more of an ideal than that it's already really out there. So what do you need to be able to know or which message gets, where you are in processing when a system fails? So there are actually 2 things. You need to know the state of the progress, so the offsets, like which data did I already process and what did I not process yet. And you need to know the state of the data itself. So if you're doing stateful computations like windows, you need to have the rest of that window to go on with your processing. The way most frameworks do that in a very broad description is you have your different workers. They all have some internal state in one way or another, and they're reading and writing to that local state when they are doing their processing. Then every now and then they do checkpointing, which means they use some reliable persistent storage, like for example HDFS or S3, to do their checkpointing. They checkpoint the state onto that reliable distributed file system in this case. And when something goes wrong, they restore it from there. The workers come back up, they get the state from HDFS, and they can continue processing like that. So different state stores that you can use inside workers in most frameworks are in-memory hash maps or RocksDB. In-memory hash maps are limited by the size of your JVM, because it's just a hash map that each executor has, which contains key values, and it accesses the right key for a certain message that it needs to process. It's on the heap, so that means that if you do garbage collect, it will go over all of your state. And it's Java objects, so that means it's deserialized, which is a very big advantage, because that means it's fast. You don't need to deserialize the data yourself, because it's not serialized. For RocksDB, on the other hand, it's a key value store. It's stored off the heap. So that means you don't do GC on it. It's spillover to disk, so you can use it if it's data that does not fit in your JVM. And it's serialized because it uses disk as well. So that means you have larger or longer access latencies, because if you want to access it, you need to first deserialize it before you can use it. The difference between in-memory hash maps and file system, which is something Flink uses, is in the case of Flink, they call it in-memory if your state is backed up by your job manager, and they use it and they call it file system if it's backed by something like HDFS or S3, so by a file system, reliable file system. So for Spark streaming, it was in-memory hash maps until now, structured streaming as well, but they have now a ticket open to also implement RocksDB backends, which will probably help a lot with keeping a lot of state for applications. I've also heard that Databricks uses RocksDB as well in their product. For Flink and Kafka Streams, you also have in-memory and RocksDB. Flink also has this file system one, which is actually just checkpointing to HDFS or S3. And then you have Kafka Streams also offers some custom state stores that you can use. I think Flink as well, by the way. So how is checkpointing done? There are actually 2 important terms here, incremental checkpoints and asynchronous. So what incremental means is that every time you do a checkpoint, you don't checkpoint the entire state, but you just checkpoint what changed since the last checkpoint you did. So you do it incrementally instead of doing everything every time. Asynchronous means that you do not stop all your processing threads, but that it's an asynchronous thread which does the checkpointing so that you don't need to stop all the other threads for that. Spark streaming checkpoints at an interval and doesn't do this incremental. They changed this in structured streaming where they do incremental snapshots, checkpointing and asynchronous checkpointing, and they do it at every trigger interval. So when you define your application, you need to define a certain trigger, and at every trigger they do the checkpointing. For Flink, it's also at an interval. They offer asynchronous checkpointing and also incremental checkpointing on some backends, not on all of them. And Kafka Streams is actually the only one here that takes a completely different approach. They don't really do checkpointing, but since they are so closely integrated with Kafka, they use Kafka for their fault tolerance. So they have changelog topics which they make. Your application is all the time putting data back on Kafka and reading it again. And by doing that, they know on which, by reading the changelog topics where processing was left off. So state is persisted to Kafka. These different ways of keeping state, they are, I think both of them are fine, but they are just differences in the way these frameworks work. So if we look at these results, we could say that for a use case like, for example, the fraud detector, a tool like structured streaming would offer you high-level programming language with close integration to your batch APIs, which you can use to do your machine learning. They're now offering continuous processing, so they're getting close to event-driven or implementing event-driven there. You can use a Spark cluster to process your workloads, and probably you'll have some other Spark tasks as well in most banks. For a platform monitor, something like Kafka Streams would be an interesting option to look at if you don't have already running clusters that you could use for that. So these were the questions that I talked about today. This is not an exhaustive list of things you need to look at when you have a problem at your bank, something, or at your company that you're working at. That's an important thing to address. There are many things I didn't talk about today, like, for example, the maturity of a framework. Do you expect that it will still exist in 5 years? The community around it. Is it easy to get help if things go wrong? Is it easy to do feature requests? The cost of running certain things, like where do you want to run it, on which cloud, and how much does that cost? Scalability, is that important for you or not? And there's a long list of other things that you could add here, which are important to keep in mind for certain use cases. If you want to know more, there's an interesting book that I can recommend. It's Stream Processing with Apache Spark by François Garriot and Gerard Maas. It has been released a few months ago, so it's very much up to date. It's an interesting read to know more about this topic. And if you want to work with these tools or get advice from Clario, the company I work for, you can always contact me either via email or via LinkedIn. We're always looking for people that want to learn how to use these tools. So very much welcome. That's it. Thank you.
We have a couple of minutes for questions. So please raise your hand. I see some in the back.
Thank you for the talk. There is an opinion that Flink is better than Spark structured streaming in the very low latency streaming jobs. Can you confirm this, or maybe just you have a thought about this? Is this right?
So that's a difficult question because it's very general, and it depends on what kind of transformations you're doing, because there are lots of things that happen when you deploy a job, like the way they chain tasks together, which differs in frameworks. So that's also having an effect on latency in general. So I cannot really give general answer to that. Also, if you have lots of state, with these bigger state backends like RocksDB, Flink can give you a better performance, but structured streaming is now also moving that way. So it's a bit, you need to kind of wait and see where that goes. There are some benchmarks out there that are doing performance comparisons, but there's no really conclusive view yet on in which cases which one is really the best.
Yeah, thanks for the talk. Got a question. The continuous processing, yesterday I learned it's still experimental in structured streaming. Is this, so, I mean, if you would program fraud detection, I guess you don't want to rely on an experimental
I completely
feature.
agree. It's at the moment still, is it still experimental? Yeah. Yeah, it's still experimental. Yeah. Also, not everything is possible yet in structured streaming. Like there are still some things that are not supported, like chaining aggregations behind each other. I think some things like this. So yes, it's a developing thing. So you need to keep that in mind and keep track of how that develops. Yes.
There is a cluster here. Hi, thank you for the talk. So, question about Flink and table formats like Delta Lake. Any thoughts about actually like how it could be integrated, like one with the other, like having a sync into a Delta Lake, let's say from Flink?
No experience with Delta Lakes on my side, sorry.
Thank you for the talk. A question for the deployment. Do you think it makes a difference if you deploy Spark streaming on Kubernetes in regards to the overhead for running a cluster?
Compared to what?
You meant the overhead is pretty high when deploying a structured streaming job because you have to run a cluster?
Yes.
And if you use Kubernetes, you don't have to run a cluster actually. So do you think that changed anything?
You still need your workers running, right? And your
Yeah, but they are just pods on Kubernetes.
Yeah, okay. Yeah, that's the same for most container platforms like DCOS as well. Yeah, right. But you still have that cluster running whether or not a job is running on that. So you still have idle time and some maintenance work in keeping it up with versions and stuff like that.
But you could throw these pods away and when your job is finished.
Yes.
Okay.
We'll do one last question on that side of the room, just to be fair. And let's see which. Yes.
Could you say that Apache Storm is already dead, or?
Okay.
Yes, because it's
I'm not sure
it's
if
one
I'm
of
the
the
right
main
authority
competitors.
to make any quotes on that. I do not think it's dead, but it has been taken over by Twitter Heron. Heron is a slightly improved version of Storm now, which is interesting to look at. But I do think the competition is really hard at the moment, and that there are many use cases that could be solved with other systems, which might be more popular at this moment.
Okay, so that's it for today, for this session. Please thank the speaker again.